Hi, this question is from the topic RCC structures in precious concrete and the subtopic is working stress and limit state method. The concept to be known in this one is the idealized stress strain curve, linear strain profile in the beam, volume of block is nothing but the total force and the limit state method. The concepts the question is looking for is choosing the appropriate stress block and finding its total volume. The paper setter's expectation is the student should know well about the bending of beams and the limit state method. What they test in the student is how well they are able to integrate the concepts of bending and limit state method. The difficulty is more because they need to know a lot of tiny concepts clearly. And the students' approach for this question and the questions of this kind is they should draw the stress block, mark the stress and strain values from the by choosing the data appropriately, the profile of stress strain across the depth, and they need to find the volume of the block. Shortcut is if one knows the total force, compressive force, with the partial safety factor is 0.36 FCK BXU, they can multiply that with 1.5 to get the answer, because in the question they have told without the partial safety factor. So that is the shortcut. The time it takes is 80 seconds approximately. This is not a disruptive question because it's very straightforward, and 50 to 60% of the students do it correctly. We'll start the problem. If the question asked is what is the total compressive force at the time of failure of concrete cube or cylinder, what we can do is we can directly take appropriate stress value from these familiar stress strain curves under uniaxial compression, and we would have answered the question. These graphs we are well familiar with. Now the question is how we can use this for beam. To answer this, we need to first understand how a beam deforms. Okay, let us see that. Here we have an eraser with the two lines drawn on the front face of it. Okay, now if we bend it with the fingers as shown here, we observe that what is we see here. Okay, that is the fibers represented by the blue lines here undergo change in length. The fibers that are there at the top undergoes elongation, and that are there at the bottom undergoes contraction. So obviously there will be a fiber somewhere around the mid depth where it doesn't undergo any change in length. That is called the neutral axis. Okay, so this is the eraser without applying any load. If the length is capital L, after applying a bending force like this, the top fibers undergoes elongation, bottom fibers undergo contraction. These two lines represent the plane sections across the width. So after bending we see that these two lines remain straight without getting curved. That means we are observing a very important assumption that we make during the analysis of bending of beams, that is the plane section remain plane before and after bending. So here we can see it clearly. This blue line represents the plane section before loading. This red line represents the plane section being plane even after bending. So if we want to find out the strain of a particular fiber, let's say I am taking a fiber at a distance y from the top, the strain will be equal to L plus del L divided by L. Here I have written plus or minus because plus corresponds to elongation which happened at the top and minus corresponds to contraction. That is a reduction in the length of the fiber that happened at the bottom. So in between, as I told previously, there will be a line which doesn't undergo any change, that is called the neutral axis, that is represented here. So this is a strain profile. We see a linear variation in the strain profile. This is because plane section remain plane. If we assume just Stokes' law that says stress is equal to E into strain, we can find out the stress profile also. This is what actually happens under the working load. This is the concept one use if working stress method is asked. Okay, we'll just see this further and we will slowly move on to limit state method. So these are the inferences we have got from the the experiment of bending the eraser. Top fibers are in tension, bottom fibers are in compression. We have seen the neutral axis that doesn't suffer any change in its length. Strain variation is linear, stress variation is linear under working loads. Fine, yeah. Now what we can do is, if we consider each fiber represented here as a piece of rectangular prism, arranged one on top of the other, as we can see here, then the force in a single rectangular prism will be equal to the stress in it. The stress profile is shown here. In this case we are seeing a linear stress profile. So if I want to find out what is the force in this particular fiber, what I can do is let's say if I want to find what is the stress in this force in this particular fiber, I will take what is the corresponding stress at that level from this stress profile which is drawn along the depth of the beam multiplied by its cross section area. That will give the stress, force in that particular prism. Okay, so stress in it into the cross section area of it. Okay, so now if I want to find out what is the total force, that is the total force till the neutral axis from the top, what we can do is we can find out what is the force in each fiber. If we sum it up, we'll get the total compressive force or total tensile force correspondingly. And then the cross section area is depth into unit width. Why I have written unit width here is we are just considering a slice of a beam. We are not considering the beam with the total width. We will move further and see what happens if the width is something else. Okay, so the total tensile force will be then stress at the ith fiber into depth of ith fiber into unit width. That means this fiber, if we consider the stress of this fiber into its cross sectional area plus so on and so forth, we need to keep adding like this. We can start from top and we go till the neutral axis. If we do that, what we get is total tensile force is equal to area of stress block above neutral axis into it, because basically what we are doing is we are taking this ordinate into that particular depth. Then if we come little below this ordinate into that depth, if we keep on doing that, what we get is nothing but the area of the stress block. Okay, now if the width of the beam is B, what happens? Area of the stress block, that's what we have seen here. See, we have said area of the stress block into unit width. Now we are considering a width called B. Okay, so this will become area of stress block into this width B. What does that give? That will give volume of the stress block. That's what we are seeing here. Okay, this is the volume of the stress block. If you want the compressive force, we will just take the volume that is underneath the neutral axis. If we want the total tensile force, we will take the volume of this stress block above the neutral axis, and the depth of neutral axis is given by XU here. Okay, now we need to understand what is meant by the idealized curve. Before that, we will see this figure now. See, in this figure, this dotted line starting from the beginning and moving on like this, and if we trace this dotted line, this is the actual stress strain curve of a concrete block. Okay, now we want the stress strain curve for our beam. So how we can get it is, if we multiply that with 0.67, okay, we will get the strength in the axial structure, because if we test a concrete cube, it is under a state of uniaxial compression. Okay, but in the actual structure, the concrete will be in a state of triaxial state of stress, and then not only that, duration of loading and size effects, all that matter. So they found that if the strength of the cube is FCK, only 0.67 times FCK is a strength the concrete develops in the actual structure. Okay, so that's what this second curve represents. First curve represents actually idealized curve. Why? Because for design we can't just make use of this actual curve, because then the finding out the area and volume will be difficult. So we are replacing the actual curve with an idealized curve. So it starts from 0 to a strain value of 0.002 as a parabolic one. Okay, and after this it is just a straight line. So one will ask why this is 0.002 and why this is 0.0035 here. What they did is they tested cubes of different grades and found that around a strain value of 0.002, all cubes invariably attain the peak stress value. So the peak value here we can see, this is the peak value here, right? This is the peak. Okay, then why this 0.0035 is, when a strain of 0.0035 is attained, in the beam of any grade, we can see visible cracks developing. This indicates a kind of warning to the occupants. Okay, so that's the idea behind that. So we have seen these two cases now. What is this third case is, we are applying something called a partial safety factor for the material. Okay, why this is required is, if we take 5 cubes and if we cast all cubes to the same mixed proportion, and if you test they won't give the same answers because this is a heterogeneous mix. So there is a lot of variability in the composition of the mix. So because of that, we need to underestimate the strength of our structure in order to be safe. So we are applying a factor of 1.5 here. For steel, usually we take 1.15. This is because it is manufactured in the factories where there is a more quality control possible. But as we mix and get the concrete in the sides and there is no proper quality control for that, we are using a factor of safety of 1.5 here. Okay. Now we are going to use this second curve. Why? Because in the question they told without considering the partial safety factor. Okay, that's why we are using this second curve, this second stress strain curve here. Had they not told this, we will have been using this third curve, which is called design curve. Okay, that is applying a factor of 1.5 to this second curve. Fine. So now what we have done is, we know that the strain profile is linear, so just we took the second curve and kept along the depth of the beam here. Okay, we just did that. Moving on further, now we have this strain profile. We are interested in finding out the volume of the stress block, because we previously learned that volume of stress block will give us the total compressive force in the beam. Okay, but we are yet to know what is this depth. This depth, that is x1 and x2. We need to find this. Okay, so we'll find that out and then we will find out what is the volume of the block. So now we have seen the strain profile is parabolic, starting from 0 at the neutral axis, and it keeps on moving. The value of the peak value here at this level. Okay, peak value is 0.67 FCK in our case, and at that level we have already said that the strain value will be 0.002. And when the beam is about to collapse, we said that visible cracks develop when the strain value is 0.0035. So that's what we have written here. So now what we are going to do is, we know that x1 plus x2 is equal to the depth of neutral axis, that is represented here as xu. And from similar triangles OAD and OBC, OAD is one triangle and OBC is another triangle. So we can write 0.0035 by xu. So this base by this total height equals this base by this height. Okay, that's what I have written here. So from these two equations we can find out what is x1 and x2. A lot of this doesn't take a lot of effort. This is simple, so we can directly find out from this. X1 is equal to 3/7 xu and x2 equal to x1 equal to 3/7 xu and x2 equal to 4/7 xu. So we have written it here, 3/7 xu and 4/7 xu here, right? Now we have this stress block up to say this level. It is a straight line like this, and then beneath this it is a parabolic one. Okay, so now the total volume will be equal to the volume of rectangular block plus volume of parabolic block. What is the volume of rectangular block? That is area of the rectangular block into B. Okay, what is area of the rectangular block? Simply this into this will give you area of the rectangular block, that is 0.67 FCK is this width, right, divided into depth is 3/7 xu, that is written here, into B. Okay, this is the volume of the rectangular block. What is the volume of the parabolic block? Volume is given by 2/3 base into height for parabola, area. Okay, so that's what is written here, 2/3. In our case base is 0.67 FCK, this represents the base here, and then height is this. Okay, this height 4/7 xu. Okay, that's what is written here into B. So just we need to sum them up to get the final value as 0.54 FCK BXU. So the right answer is B, 0.54 FCK BXU. Thank you.